Today we are excited to talk about the archaeological sampling experimental laboratory model with the person who created it. So before we start, could you please introduce yourself? In fact, tell us a bit about your background and what led you to develop this model.
Sure. My name is Dr. Isaac Ula. I'm an associate professor of anthropology at San Diego State University. I developed this particular simulation model for two reasons. The first is I teach students, archaeology students now, and I've noticed that they have difficulty understanding sampling theory. And it's really important in archaeology that we have proper sampling frames because we're dealing with very difficult data types. We have limited time and resources to do excavations and pedestrian surveys to find archaeological material. And when we find them, the record itself is incomplete and often missing large quantities of data. So we want to do the best that we can. But our students often are not well versed in probability and mathematics and statistics and that kind of stuff. So I created an early version of the tASEL model basically as a teaching aid so that students could do little experiments in a lab in our class and get a real personal understanding of the impacts of choosing different types of sampling strategies. Once I started doing that and using it in class, it became clear that this could be useful in a wider arena within archaeology. An area that I've worked a long time in is household archaeology. That's excavating houses and trying to look at artifact patterns within the floors and around the houses to understand how people used their domestic spaces in the past. And we particularly are interested in very small artifacts. We call these micro artifacts or micro refuse. You can imagine them as like breadcrumbs after making toast, and where you make toast in the morning, there's going to be more breadcrumbs. And especially if you compound that over potentially hundreds of years of people living there, you can get a real understanding of their habitual uses of their space by analyzing the patterns, the spatial patterns of these small artifacts. And in this arena, there's been a big debate about how much is enough. How many of these little artifacts do you have to find to be able to quantify them to a reliable degree so that you can say these are the real patterns? And some people have said, well, it's too hard to get enough of a sample, so we shouldn't even bother doing this. And over the years, I've been working to show that that's not necessarily true. And I realized that tASEL could be used to showcase that there is a way to find out how much sample is enough to do what you want to do. And so in an academic sense, that's how I developed out the tASEL model that exists now. And that's the first application that I've started working on in terms of writing it up for academic publication.
So I believe you explained about the main goal of this model. But my question can be, why it's important for archaeology, and how do you see this changing the future of archaeological surveys?
Thanks. Yeah. So firstly, there isn't a accepted single sampling strategy in archaeology. There are a couple books on sampling, a couple books on survey, some books on excavation. But generally what happens is that students kind of learn one way to do it, and it may be correct under certain circumstances, but under the wide rest of them, it's actually not the best sampling strategy. And archaeologists, for whatever reason, often learn this way. They learn the one way to do it, and they just apply that to every situation that they meet. I think tASEL has the ability to show from an early learning stage all the way through a research planning phase as one progresses, that there's more than one way to do sampling, and that with some forethought and a planning tool like tASEL, we can design sampling strategies that are more appropriate for the data spread that we think we're going to find, that are more efficient for our time and for our budget, and that lets us do our work more scientifically. So I really think tASEL has the ability to do that as a suite of other tools that I'm also working with some colleagues to develop, called Space, which is supposed to be an online suite of tools for archaeologists to plan their survey. I can't remember the full acronym, but it's about survey allocation of effort, basically, and to figure out how correct our data and our sampling frames are as we move forward.
I believe creating something as complex as this model must have had its challenges. So, what were some of the main hurdles you encountered while developing this model and the process?
That's a great question. So NetLogo is something I've dabbled in, but most of my programming has been in other programming languages, particularly Python. And so when I wrote this model, it was my first full-blown NetLogo model that I wrote from scratch. So I had to wrap my head around Logo, which wasn't terribly difficult because I know how to program already, but it was different enough where I had to figure some things out. So beyond the technical leap into NetLogo, which I've now used multiple times, what I really wanted to do was to create an interface that was flexible so that you could use it in educational settings so that students wouldn't be bewildered with how to use it, but that also allowed it to be used in research settings. And so that was actually the biggest challenge for me.
Thank you. Moving on to the outcomes, what are some of the main insights and findings that have come from using this model?
I applied it in a case study. I'm currently writing it up about micro refuse. And for there, I ran a few experiments where because you can have multiple kinds of artifact distributions in tASEL. So I did one with a diffuse random sampling of artifacts across the little world and one that was clustered. And I ran several different standard types of sampling strategies, grid-based, random, and then I iteratively moved those things and changed the size of the grid, using the experimental tools in tASEL, something like 10,000 different iterations and moving them around. So we had a lot of different experiments, and tASEL and NetLogo makes that really easy with behavior space. You can just run through a bunch of different repetitions of all this stuff. And then you can pull those data out and post-process them. I use scientific Python to do that with pandas and the graphical package called Seaborn. And I presented this at the Society for American Archaeology meetings a couple years ago, showing basically that the grid-based methods that archaeologists always use are the least successful methods for sampling both the random and the clustered artifact distributions, and that in fact, by just randomly, literally, you could throw darts and let them land and use those as your samplings, and you would do a better statistical representation most of the time. And I showed that even if you move the grid spacing around, it's still almost a uniform distribution of getting it very wrong to getting it basically right, on either side of the curve. It's not a bell-shaped curve. It's more just flat. But if you do a random sampling system, you get that bell-shaped curve. And depending on the number of units, you can shorten the tails and basically make it more likely that you're going to be correct a larger percentage of the time. So I think visually that was a useful thing for people.
So, what's next for this topic? I mean, are there any follow-up developments in the pipeline that we should be looking out for?
Yeah, thanks. So firstly, I'm writing up the paper currently. It's mostly done, so I hope to submit it soon. Showcasing the results I just talked about, with micro refuse. We have another paper that should be coming out soon in the PCI journal, which is the Peer Communities in Archaeology, about the larger project called SPACE, the Survey Planning and Allocation of Effort. That's what it stands for. And that particular paper is about another tool that we're developing. In this case, it's developed in the R programming language. And it is, again, to simplify these statistical approaches to planning your survey effort. And in this particular case, it's how closely people should stay next to each other based on a model of how we can detect artifacts. Basically, your ability to detect artifacts falls off as further you go from your line of vision. And we do actualistic experiments in the field. We have people literally walking, and we seed artifacts, and they write down when they see them. So we've used that actual empirical data to prime that, and it gives you a sense in these particular field conditions with this type of vegetation, these kinds of artifacts, and your actual crew members, how good are they at finding the actual artifacts? And that tells you how many times you need to resurvey a field, how close people need to walk to each other, and it helps you plan how much time and effort it's going to take to do the work that you want to do it.
So you've made this model available through comsys.net. What were some of the challenges in the archiving process and I mean making it accessible to others?
Yeah, so firstly, I believe in ComSys's mission. I really have enjoyed the ability to access a centralized library of various types of model code. So I was familiar already with ComSys, and the submission of the code initially wasn't too difficult. I self-host a lot of code on GitHub. I use Zenodo and the Open Science framework and a few other things to do this. So using ComSys wasn't any more difficult than that kind of stuff. So that part was very easy. The most tricky thing for me was to figure out the peer review process for the code. And I think I made a mistake in the most recent one I submitted. I didn't realize you weren't supposed to publish the version before you asked for the peer review. So I have like multiple versions of this model on there, and they're only there because I made mistakes in the peer review process. It should just be one version.
Yeah.
But it is what it is. So there's 2 or 3 releases of tASEL as it went through the peer review process.
Thank you so much for sharing your insights and experiences with us today.
Sure. Thank you for having me. Appreciate it.